Welcome. My name's Waleed Kadous, and with me is Marc Stogaitis. We're members of the Android location and context team, and we're super excited to be talking to you today about how to make your apps context aware. And we're going to explain why we think now is the right time to do it, some of the tools that are available to help you do it, some things to watch out for, and finally, something I'm really excited to do with you today, which is to share a vision of what the future will hold as far as this is concerned. So I want you, next slide, please. I want you to imagine that instead of presenting at Google I/O 2015, I'm presenting at Google I/O 2020. And I want to describe to you what my day so far has been like making it here to Google I/O 2020. I'm sleeping comfortably in my bed in my house, and my phone alarm goes off. And it's not that I programmed my phone to go off at that particular time. It just knew that was the right time to wake me up. It knew I had a late night before. It knows the traffic it will take to get to Moscone. It knows that I like to have showers in the morning, so all I said to it the night before was, wake me up in the morning. Now, I pick up my phone, and of course it's automatically unlocked because it knows exactly who I am, and it knew that it spent the whole night next to the bed. But even before I've got out of bed, the house has started to come alive. My room has started to warm up to a comfy 72 degrees. The lights are slowly coming up to welcome me into the day. And of course, the coffee maker is going, because who knows where we'd be without coffee. As I sit down in front of my breakfast, my tablet is there waiting for me. As soon as I sit down in front of it, the content for the day appears, all my events, all the exciting talks I'm looking forward to at Google I/O. And not just that, it's suggested some activities for me that it knows about what I'm interested in. So for example, it knows I love Asian art. It knows that I'm in San Francisco, and it knows that the Asian Art Museum is open late on Thursday nights, which it is. You guys should go check it out. But it put all of that together for me so that I can just see the day ahead of me. And just as I'm finishing checking out stuff, my housemate joins me, and he's also enjoying his morning coffee. And as we're sitting there, just as we're finishing the cup of coffee, we get a buzz that says that our car is waiting for us downstairs. And sure enough, we go downstairs, and waiting for us is our self-driving car. We hop inside, excited about where we're going to go today, and we notice that the music comes on. And the music is specially selected. It just so happens to be the music that both me and my housemate like. And to be frank, that level of overlap is not so large. But we'll talk about that another time. And then just as soon as it gets to Moscone, I notice that my watch buzzes. And on my watch, I notice that there's a map that takes me directly from the curbside in through the front door, which of course I don't need to swipe my badge or anything because my watch already knows who I am, and I can share that with the devices around me. And it takes me up the stairs, turn left, turn right. And as I come to the auditorium, I get a buzz from my friend that says that she's sitting in the audience. She's come in from New York. I don't get a chance to see her very often. And my phone guides me directly to where she's sitting down. I sit down next to her. We get a chance to catch up. And we're ready to take in a day full of knowledge and exciting information about what's happening at Google I/O 2020. Now, the question in all of this is, that sounds a little bit sci-fi, a little bit crazy. But I want you to disassemble that. And I want you to think about the interactions between the device and the user as this whole experience happened. I want you to think about how many unnecessary interactions were avoided. I want you to think about how many times the system reminded me in context when it was useful to me, and how it brought new knowledge to my fingertips that I didn't really even ask for, but I knew that it was very useful. And how it was able to enrich my life by letting me sleep in for the maximum amount, by making me feel more comfortable in the morning instead of a rude awakening. So I really think that those components there that we mentioned, that type of simplification of a person's life, that simplification of interactions, those things we can build today. There's no obstacle to us doing that. And what I'm going to try to convince you of is that not only is it possible, we already have some applications that we've built and some other people have built that show these type of contextual experiences. And let me explain to you why I think now is the perfect time to do it. We have in our pockets an amazing platform. I don't think sometimes we're so involved in the day-to-day of things, we don't take a step back to just think about how amazingly powerful our platforms are. So inside your phone is a processor that can process 8 billion computations a second. Not only that, but it's full of sensors. It's got accelerometers and gyroscopes and barometers and magnetometers. Some phones even have humidity sensors. But that's never really happened before, that we've had that level of sensors available with us in that way, in an always-on fashion. And we can use those sensors like the accelerometer to determine things about the user's context, like if they're running or walking or driving or cycling. There's also other rich sensors on there, like the camera and the microphone, that can pick up cues that we can use. And combine that with the huge variety of techniques available for communication, like cell and Bluetooth and Wi-Fi and GPS. And GPS, when you think about it, is kind of a little bit crazy. It allows us to talk to a satellite that's 20,000 kilometers away to work out where we are. So we have to ask ourselves, have we really taken full advantage of this platform in terms of really relieving the pressure off the user in terms of memory, in terms of simplifying their lives and easing the interaction? And I think the answer is that right now we have this very, very large opportunity ahead of us. Basically, in the history of computing, we've never had this combination of sensors, communication, and computing power. And we can use that power, those sensors, that ability to talk to devices nearby, to understand the user's context. I think all of you can think back to the keynote and what Aparna was telling us about Google Now as an example of this. And we can use this idea of understanding the user's context to simplify interactions, to augment human memory and knowledge, and also to make people's lives just a little bit better. And I mean, when I think about simpler interaction, I just think back to the broken model we have. One of our primary means of interactions with devices is that we took a 19th century technology, which is the typewriter, which was used to bang like letters onto a page, and we shrunk it down and tried to get it into a phone. And that's the metaphor that we use. There's got to be a better way, and we should be able to use the sensors on the device to help take that load to use those keyboards off the user. So where we're going to go from here is we want to walk you through our experiences building these types of systems. But this technology is still very new. So there's a couple of things, or in fact, to be exact, 3 things that you need to pay very careful attention to. And finally, I want to map out what the future might look like between here and 2020, that Google I/O talk that I hope to see all of you at in the future and be here presenting again. And with that, I'll hand over to Marc, who will walk us through some of these experiences.
Cool. Thanks, Waleed. So Waleed described the power of modern cell phones, and he also set the stage for what 2020 might look like. And what I'm hoping to do is to show you what's possible today. I think a good example is something that happened to me a couple of months ago. So as I was driving to a restaurant, I used Google Maps to help me navigate. And after I parked, I walked over to the building, and just as I walked in, I realized that I didn't pay attention to where I parked my car. Now, that's a terrible feeling that I'm sure some of you have experienced before. Now, luckily, I was able to swipe over to Google Now, which had a card indicating the last location of where I parked my car. I think that's a great example of the type of contextual experiences that can be built today, and I'd like to show you how to build these. So usually context is broken down into 3 layers. We start by taking sensor data, like that of an accelerometer or Wi-Fi, and then build algorithms on top of these, which take raw sensor data and turn it into higher level signals, like location or user activity. And then finally, we use those signals to build features and apps. So let's look at these 3 layers in a little bit more details. Context starts with sensors. Sensors are what allow our devices to understand the world around them. They allow them to break out of the digital world and into the physical world, the world that you and I live in. And I think a good way to think about context and sensors in general is to think about human senses, since we're really good at understanding the environment around us. And building up this strong mental model of how sensors work is important because a lot of context is built on top of these. So something that's helped me with this, is also a little bit of fun, is to ask myself, what if I had Android sensors instead of human senses? How would I perceive the world around me? Well, I'd see with a camera, a light, and a proximity sensor. I'd hear with a microphone. And I'd keep my balance with an accelerometer and a gyroscope. And I would use these sensors to understand the world around me and make decisions based on what I see. Now, as a human, I'm pretty lucky. My brain takes care of all this sensor processing for me. But how can we do it on Android? Well, algorithms need to be built on top of raw sensor data to make sense of what's happening in the real world. And there are many challenges here. So you have to come up with ways of fusing noisy and sometimes conflicting sensor data. We have to put together large data sets that allow us to train and fine-tune models. And we also have to come up with ways of enabling and disabling different sensors so that we can manage power consumption. Luckily, we've tried to make this as easy as possible. So we've built several Android services that take raw sensor data and turn it into contextual information. Now, these include the activity recognition, places, geo-fencing, and the Fuse location provider APIs. And I'll talk about these in a little bit more detail in just a little while. So the key takeaway is that these allow you to receive context information in your apps with just a few lines of code. All of the processing is handled under the hood, so you get to focus on what really matters, which is the user experience in your apps. A context can sometimes be a little bit abstract, so my goal for today is to make it as concrete as possible. And to do that, I'll try something we haven't done before, which is to take launched Google products that make use of context and show you a behind-the-scenes look at how they work. So which APIs they use, how those APIs work, even which sensors they use. Now, hopefully, this will help illustrate what's possible today. So let's start with Smart Lock. And when I went home for Christmas, my mom asked me to enable a password on her device. She saw that I was using a swipe to unlock my phone. And after about a couple of months, she emailed me and said, how do I disable this? Now, basically, she found that having to do this every single time she needed to use her device was just too cumbersome. So everyone will weigh the pros and cons of security versus convenience a little bit differently, but this exposed an underlying problem. When it comes to unlocking your device, there are only really two options. You either disable security completely, or you enable it and have to perform some kind of action every single time you use your phone. So is there something, can we use sensors to make this better? Well, it turns out there's a lot that can be done here. And one example is on-body detection. So the idea behind this was pretty simple. If you're using your phone, and you put it in your pocket, and you walk around for a while, when you take it out again, it should still be unlocked. Your phone should be smart enough to know it's been in your continuous possession. So how do we make something like that work? Well, it starts with accelerometer data. So what you see here on the left is the accelerometer coming from a phone that's in a user's pocket. On the right is a phone that's just on a desk, not on the user. So you can visually tell that they're pretty different. And you basically, even if a person's sitting fairly still, there'll still be micro motions that can be detected over time. But is this enough to build something like on-body detection? Well, not quite. When it comes to context, there are usually many real-world variations to deal with. One of the problems that came up was that, let's say you're sitting in a cab and your phone slides out of your pocket. We need to know that it's not on you anymore so that we can lock it. But the accel that comes out of a phone that's in a car looks extremely different than that of a phone that's just sitting on a desk. So we needed something that could tell us that the phone was in a vehicle so that we could train situation-specific models. Well, in comes the activity recognition API, and it's the first context API I'd like to introduce. It works by fusing sensor data to detect the user's current activity. The way it works, it takes basically, we took some accelerometer data and used machine learning on top of that data to try and predict the user's current activity. And we've also added new signals recently, like the use of Bluetooth, and trained new models to make the detections run faster and also improve the accuracy. So let's look a little bit at how it works behind the scenes. So what we did is we asked Google employees to record over 65,000 sensor traces where they would label the activity they're doing as well as the carry position. So they'd say something like, I'm on a motorcycle and the phone's in my backpack, and label and gather sensor data. And we then extracted features from that sensor data and trained machine learning models that could predict the user's current activity. And after that, we took those models and made them run directly on the phone without needing any server interaction. This saves battery, bandwidth, and also makes the detections run faster. So this is kind of fun. So Kevin, an engineer on our team, went out and recorded sensor data along with videos of what he was doing. And the goal is to basically look at the sensor data and try and figure out, was he walking, was he on a bicycle, or was he in a vehicle? And if you look at this one, this is coming from the accelerometer data from his phone. So you can see there's kind of a couple of big spikes that happen. Those are usually an indication that somebody's moving their leg. Either they're walking, and each time they hit the ground, there's a big spike that happens, or maybe they're biking. Each time they cycle around, there's a big spike that happens. If you add another sensor, like the watch accelerometer, all we see here are a lot of vibrations. We don't really see any big spikes like you'd expect to see if somebody was walking. So these types of vibrations, you'd usually expect to see if somebody's holding onto the steering wheel of a bicycle and just kind of feeling the bumps in the road. So let's take a look at what he was doing. Well, he was in fact biking. So this goes to show that if you use accelerometer data, it's a pretty good indication as to what the user's activity might be. Let's take a look at another one. So this one, it looks a lot like walking. So the top graph, which is coming from his phone, has a lot of these spikes that are pretty periodic. And the watch also has kind of very similarly timed spikes. So he's basically walking. That's what it looks like. So that'd be my first guess as to the activity. But if we add one more sensor, which is a barometer, things get pretty interesting. So a barometer senses atmospheric pressure. And basically the way it works is, the lower you go down in altitude, the more atmosphere there's on top of you and the more pressure your phone will sense. It's a little bit like if you go underwater. The deeper you go underwater, the more pressure you'll feel. And the same thing happens here, and your phone can sense that. So here there's kind of a continuous upward spike in the barometer, which means the user is actually decreasing in elevation. So we have somebody who's decreasing in elevation and also doing something like walking. So what activity is he doing? Well, he's going down some stairs. So I think it's a good example of, like, if you add another sensor like the barometer, you can better detect what's happening in the real world. Let's look at one last one. So Kevin, when he showed me this one, I had no idea what this was. I've never seen something quite like this. So he told me, well, OK, I'll give you a hint. I was playing a game, and I had a gamepad that I was playing with. I said, OK, well, the first part of this looks a little bit like running, but then there are these huge spikes that happen in the middle graph that I've just never seen before. So let's look at what he was doing. OK, he's playing on a gamepad. And then, oh, he starts using his fists. OK, now it makes sense. He's cheating. If you've ever played this game before, you've probably tried that yourself. But it's a good example of why we introduced an activity called unknown. This basically allows our classifiers to say, you know what, this kind of sensor data, I've just never seen it before, and I don't want to make the wrong thing and say, oh, you're biking or you're running, so I'm just going to guess unknown. So in summary, on-body detection works by taking accelerometer data, as well as the activity recognition API, to detect that a phone was in a user's continuous possession. It saves users over 20 unlocks per day. But can we save even more unlocks by using other context signals? Well, the answer is yes. So for me personally, if I'm at home, I'm comfortable having my device stay unlocked. But if I go to an airport, I want it to lock in case I lose it. So different places have different levels of trust for different people. And the Trusted Places feature allows you to keep your device unlocked in places that you trust. So let's see how it works. Well, it makes use of the second context API I'd like to introduce, which is the Places API. This API makes it really simple to get information about the places around your users. And it also contains a component called a place picker, which makes it easy to launch an interactive map that allows your user to select a nearby place. So let's look at a little bit of code to see how it works. Well, to use the place picker API, you simply create a place picker builder, and then you call start activity for result. When the user selected a place, you'll get a callback with the details of the place, like its name and address. It's really that simple. And the other API used by this Trusted Places feature is called the geo-fencing API. This API fuses location as well as activity to detect and to give your apps a callback whenever it leaves or enters a particular region. It allows your apps to respond to changes in the user's location while keeping battery consumption to a minimum. And for this feature, it was used to unlock my device just as I arrive home and lock it again when I leave. So to use it, you set a circular region around an area, and then you decide if you want to be told about entries or exits of a particular area. And we also added a new transition type called dwell. This allows you to say, I want to be notified only when the user's been inside of the geofence for a specified amount of time. It makes it easier to distinguish between the case where somebody walks by your geofence or actually stops at the place that you're interested in. So in summary, we have the Trusted Places feature, which uses a place picker as well as geofencing to make sure to unlock your device in places that you trust. And we had this feature, which uses a lot of very kind of location-based. And we had the on-off body detection, which is using accelerometers quite a bit. So what happens if we use these two sensors together? Well, we can build a feature called where did I park my car, which is one I mentioned earlier. And what I love about it is that it's completely automatic. I don't have to remember to take my phone out of my pocket and press a button every single time I get out of my car. So how does it work? Well, it makes use of the Fuse Location Provider API, which is an Android service that uses Wi-Fi, cell, GPS, accelerometers, gyroscopes, magnetometers. So basically a huge, huge amount of sensors to try and figure out the location of your device if it's indoors or outdoors. It also provides multiple controls for developers to allow you to tune for higher accuracy or better battery consumption. So let's take a look at how it was used as part of this feature. Well, we started with the activity recognition API and looked for whether or not the user was in a vehicle. And once you detect the user's in a vehicle, we then register for the Android tilt sensor. This is a sensor that can really, at like super low latency, detect that a user went from sitting to standing. And it helped reduce the amount of time it takes to detect that a user came out of a vehicle. And then finally, once we detect the user just got out of a vehicle, we use the Fuse Location Provider API. And then there you have it, the location of where you parked your car automatically detected. So I'm a huge fan of the quantified self idea, and that's why I love the Google Fit app. It tracks my steps. It tracks my bike rides as well as my runs. And it does this completely automatically. I don't have to remember to push a button every time I go out for a bike ride. And to do this, it makes use of many APIs. So it makes use of the activity recognition API, the fuse location provider API, and even the sensors API to track things like heart rate. And after using it for about a couple of months, I noticed that on weekends, I would routinely miss my step goal. So I thought this was a really interesting insight for me that allowed me to adjust my routine. And once I did, I noticed a significant improvement in my skating stride whenever I played hockey. So I thought that was great. But now, after my legs were super strong from all that hard walking, there was a new limiting factor for me, which were my lungs. They would just burn after a really hard skate. That kind of high level of intensity just isn't reached by walking. So we asked ourselves, what can we do to make fitness a bit better? Well, new devices bring up new possibilities. Android Wear is great for context. Since it's packed with sensors, it's always on the user, and it's at a known fixed location. So we decided to study sensor data to see if we could detect some of these commonly known activities like push-ups, sit-ups, and squats, which have a really high level of intensity. Well, it turns out it's doable. So here's an accelerometer graph of what doing a squat looks like. So each time the user does a squat, you can see this huge spike that happens. And basically, we can write algorithms on top of this to detect it. So I love staring at accelerometer graphs, and I could do it all day. But I think a live demo will be a little bit more interesting. So please welcome Barbara, the engineering lead of this project, onto the stage to show us this in action.
Thanks, Mark.
Can you switch over to the wolf vision, please?
Yes. So today, I'm going to do some workout on the stage and show you how activity recognition can automatically detect what workout you're doing and also how many reps you've done. First, I'm going to do some squats. And while I'm doing it, you should be able to see the count on the big screen. 1, 2, 3, 4, 5. Cool. So, yes. As you can see, I did 5 squats, and while I was doing squats, the count incremented one by one. The count you see here is synced from my watch directly over Bluetooth, so the detection is all happening on the watch. You may also notice we only started showing the count after I've done 3 squats. This is because we want to differentiate between a real squat versus a random arm swing. OK, the accuracy for squats is pretty great. Now let's take a look at sit-ups.
Do you want to move back a bit?
1, 2, 3, 4, 5. Awesome.
Yeah.
Thanks. Back to Mark.
Cool. Thanks, Barbara. All right, can we switch back over to the slides? Thank you. All right, so we saw how, that was a really cool demo, by the way. So we saw how Smart Lock, Find My Car, and the Google Fit app make use of context to improve their app experience. Now, these are Google-specific use cases, which were useful to use as examples, since we could really dive into the details. But what I'd like to leave you with now are a few examples of how you can use context in your own apps. Switch. Thank you. So yeah, context can be used to simplify interactions with the device. So Waleed mentioned earlier how keyboards are really small and hard to type on. Well, one example would be that if you have a chat app, you can automatically fill in the name of a nearby place as the user's typing to save them some keystrokes. You can also write a feature that would simplify sort of the output of the device. So if a user is driving, you could automatically read text messages out loud to make driving a little bit safer. Slides are being a bit slow. And you could also do things like, OK, we'll go without the slides. So OK, you can also use it. Other ways of simplifying interactions would be if, say, your user arrives home, you can automatically turn on the lights. You can also use it to simplify sharing. So one example would be that if you have a text messaging app, as your user is driving, you could let other users know that they're driving by putting a little icon that says, this user is currently driving, and then it can save them from having to receive, send out a text message when that user is already busy. It can also be used to, let's say your user just went out for a run. You could say, all right, let me fill out a post with the distance that you've traveled. That way you don't have to actually go in and say, okay, hey, I just ran 10 kilometers. So maybe make sharing a little bit easier. And another example would be an activity leaderboard. So something that I like a lot from some of these fitness products is that they show me, here's how much you've walked versus other users. You could do a lot more of that. So say, for bike rides, you could show this is how many miles your friends have biked versus you. And then make, basically, keep things a little bit more interesting in terms of challenging for your friends. You can also use it for use cases that are related to entertainment. So let's say that I go out for a run. Well, if I hit a really tough part of a run, maybe you could play the song Eye of the Tiger to keep things interesting. It can also be used for games. So for example, you could write a game that's a treasure hunt based on activity and location. We're getting stage directions as to whether or not we'll get the slides back. It's OK. This part is actually pretty non-visual. The next part will be, I think we'll need the slides back. So other entertainment use cases. For example, you could do movie recommendations. So if I go out and I go to a ballpark, and then I get home, you could recommend, hey, you might want to watch the movie Field of Dreams. And it can also be used in quantified self use cases. So I mentioned how the Google Fit app is great for quantified self, especially around fitness. I think there's a lot more that can be done here. For example, you can show users, this is how much time you spend on commuting. And here's how much it was this week, here's how much it was last week. Hey, we're back. All right. So yeah, here's a quantified self use case. So basically, you show your users, this is how much you've done in terms of commuting this month and last month. And then show, hey, maybe if you left a little bit earlier on this day or this day, you'd actually be able to save extra time. You can also show it for restaurant visits. So if let's say you show me a summary of this month, how many times I've visited restaurants versus last month, I can use that to compare and maybe optimize my life a little bit. And finally, it can be used to explore and discover the world around your users, like showing nearby events, or even just as I walk up to a restaurant, you can show me this is the menu for this restaurant, here are the best items so that I can compare. And of course, the best examples will come from you. So there you have it. I hope that going through these examples has helped illustrate the type of contextual experiences that can be built today. And I look forward to seeing these in your apps. And now Waleed will speak to the challenges of building contextual experiences.
Thank you, Marc. So it's important to realize that these technologies and the ideas that Marc presented to us are really in their infancy. So we're at a very critical stage. You can really build some awesome stuff, but you need to pay very close attention to a couple of things because the technology is so new. It's not like, say, graphical user interfaces that have been around for quite a while. So it's really important that you pay attention to a few things. And those three things are user trust. In other words, you need to establish a relationship with your user to help them understand how you're using sensors and what the application is doing for them. Secondly, recovering gracefully when things don't go right. And finally, and perhaps most challengingly in the current age, battery life. So let's talk about user trust. Really here, there are two key rules. The first one is to collect only what you use. It's so tempting with the huge range of sensors available to say something like, give me everything you got. But really what that leads to is it leads to user confusion. And we've seen that ourselves. We've seen flashlight apps that require fine-grained location, which doesn't make any sense at all. And the other really important principle is to explain how you're using the context to benefit the user. And generally what we've seen is if you can present to the user the benefits of sharing these sensors like GPS and an accelerometer with you, then they will understand and they will come with you on the journey as you launch the app. So let's go through some examples that we have in our own products in Google. The first one on the left shows the trusted places. So what happens is the first time that trusted places triggers, after you've installed it and enabled it, is it will have an interstitial here that explains, by the way, we unlocked right now because we knew where you were. You were in a particular place, and now we've communicated to the user how we're using location to make their lives better. The second example comes from the on-body detection that we mentioned earlier. And that's really about explaining to users how we're using the accelerometer. and we have a short explanation with cute little graphics that say, hey, this is what we're doing. And we've really found that this helps users to understand and come along with us on the journey as we make apps more contextual. The second principle that we have to adhere to is really recovering gracefully. Now, as Marc showed you, these are all machine learning algorithms. No machine learning algorithm is perfect. So for example, if you're driving really slowly, it's going to be very hard to tell that from cycling. Or for example, if you think about choosing a place, maybe we won't get you at exactly the right restaurant, but we'll get you next door, right? So we have to design with the idea and change the user interface and interaction to have capability for that. So for example, when you look at Google Fit, although we automatically detect the start and end of things, it's really important to provide the user a way to correct that. Or think about the place picker. When you look at the place picker and we're giving people a bunch of options to choose from, ideally, we wouldn't even give them the option, right? We just say, you're definitely at this place. But what we do is we offer a couple of other options so that the user can choose the correct one in case we didn't quite get it right, but we were close, right? And then the third example is to do with think back to on-off body detection and trusted places, and really contemplate what we did there. What happens if we get it wrong? What happens if we think that the phone was on a desk, but it was actually in their pocket? Well, what might happen is that we might ask them to unlock one more time. And is that so bad? At least we've had the benefit of being able to reduce the number of unlocks that they have to do on a regular basis. Now, this is perhaps the most challenging thing that you will face as you try to make your apps more contextual. And I think it's important to us to recognize the difference between the way that these contextual apps work and normal apps work. Most of the apps we develop, but not all of them, are basically foreground applications. And when you're a foreground application, what you do as far as power doesn't really matter so much because the screen's going to be the dominant factor in your power consumption. And so what that means, and in addition, most of our apps, maybe the user uses it for 10 minutes a day or 15 minutes a day. It's not like they're using it for 15 hours a day, right? And in fact, if you look at the statistics, the average phone is on for 4% of the time. Now we have to switch our mental model. And we have to think of, instead of these huge spikes for short intervals, we have to think about sipping a little bit of power all the time. And that means we have to adopt some new metaphors and ways of thinking about things, and in fact, change the way the hardware is designed to facilitate that particular use case. Now, the great thing with Android is just how flexible it is. It's an amazingly flexible system, and you can do things on Android that aren't even possible on other platforms. But it also means that that gives you a lot of rope to hang yourself with. So you have to be super, super careful in how you use these things. So what we've tried to do with the APIs that we've provided is that we've tried to give you powerful abstractions that aren't very power hungry. And that gives you a lot of capability to address the common cases. But as I mentioned, the beauty of Android is just its flexibility, and you can always go off and build your own contextual experiences. So just to give you an idea of like what we do in our labs, now we're designing APIs for the entire ecosystem, so we put a little bit of effort into this. This shows our power regression testing lab. And what you can see there is a bunch of monsoons. Those are devices for measuring power very accurately. And what we do is every time we make a change to the code that we make available to you, we run it against these devices to make sure there are no regressions. Now, again, I want to emphasize that you can always do your own thing, but you do need to pay attention to power because it's one of the greatest challenges. So if you want to get power right, there are two key principles that we've seen. The first one is you have to make the hardware do the heavy lifting for you. And we'll talk a little bit about the design patterns, the subcategories there. And the second thing is to really think about what does your application really need in terms of quality. So to really understand making the hardware do the hard work for you, we need to kind of step in and understand a little bit about how things used to happen and what happens now. So traditionally, the model in Android was that you had sensors that themselves might be quite power efficient. Like your accelerometer, it's pretty power efficient. But your application processor that actually does those 8 billion calculations and renders the screen and makes your game run and gives you no jank and all of that kind of stuff, that thing is actually pretty power hungry. In fact, it consumes a very, very substantial amount of power. So the game here is to keep that application processor on for as little time as possible. Now, the issue is that if you have a sensor, even if the sensor is low power, let's take you back to your college days and draw one of these sequence diagrams. What happens is that the sensor sends the update to the processor. The processor sends it to your app. So each sensor measurement you get, and you might be getting 25 or 100 sensor measurements a second, the processor has to stay awake, and it never gets a chance to go to sleep. So what we did is we changed the design of the internals of Android. And we said, what if we can put some low-power hardware in between the sensors and the application processor? This will give us a mechanism to really get to low-power possibilities. So effectively, what we have is something like this. You send the sensor data to this little low-power thing, which we will call a hub for now. And instead of it waking up the main application processor, it's going to bunch together a bunch of measurements, send them as one package to the processor, and the package then delivers that to your app. In the case of accelerometer data, we've seen this cut our power by 80%. So using this feature is very, very power advantageous. And in fact, this is what we rely on for our activity recognition to make it even more power efficient. Now, we already put this low-power hardware box in the middle of it. But what if instead of just gathering up a bunch of measurements and shipping them off in one go, we actually put more intelligence on there and ask that the hardware check for conditions to be true or false, and actually start to put programs in there? Then what's possible is that you could actually check for the geofences in the hardware. And some of the versions, some of the Android devices in your pockets actually do hardware geofencing, which is much more power efficient than software geofencing. And think back to the keynote where we were talking about doze mode. Doze mode is built on something called significant motion, which watches the accelerometer all the time to see if the position of the device might have changed in a significant way. And by using that sensor, we were able to really extend the battery life of the device, and it's really enabled us to build some very impressive features. So we talked before about design patterns and making the hardware do the heavy lifting. But the other thing to think about really carefully is, what does your application really need? And I want you to think about a weather app and an indoor navigation app. Clearly, for a weather app, I don't need like the most accurate location. I just need city-level location to get what I want. Now, the fused location provider gives you options as far as power: high quality, balanced, and low power. And in this case, we would choose low power. But compare that to an indoor navigation app. The user's looking right at the device. I want the highest quality I possibly can. So then I would ask for high power. And not only does this apply to accuracy, but also to timeliness. For example, if we have the same situation, do I really care if I show the city for 5 minutes or 10 minutes after I've left that city and moved on to, say, Berkeley instead of San Francisco? We think we can probably tolerate that. But if you show the user's location 50 seconds after they were there, that's going to be a pretty horrible experience. So it's really about you telling the system what you need in terms of features. So those were the difficulties we have to overcome. But what I'm really excited to share with you in our last few minutes together is what I think is going to happen in the future, because I really think we're on a good track to 2020. So there's, of course, going to be a large range of incremental improvements. Location will get more accurate, and the range of activities we detect is going to get broader. We're going to detect going upstairs and downstairs and up elevators, and maybe even more extreme things like playing golf or cooking dinner. But there's also 3 critical step functions that I want to outline to you folks. The first of those is improvements to location. The second one is moving to a multi-device world. I think you remember Sundar's conversation today about Brillo and the Internet of Things. And finally, opening up that low-power subsystem that we've just been talking about. So let's dive right in. So I really think that location will get very, very much better in the coming while. I think one of the biggest weaknesses with location right now is it's not available indoors. And I think we have some ways that we can improve that. Now, what I want to highlight is in the next slide, I'm going to show you a video. This is not close to production. It's way too power hungry and too flaky and too lab-like to launch. But I wanted to show you what we've been working on in our lab. What you can see here is a diagram of one of our labs. And the green line shows ground truth. And the blue dot shows what we're able to compute in terms of location. And the most impressive thing about this is we don't use any sensors that aren't already on your device today. You can see it's tracking pretty bloody accurately. It's about 2 or 3 meters off. And that's pretty impressive. And we're really excited about working to make this a reality in most people's devices. Imagine what you could do in terms of geofences with something this accurate. The second point we talked about is multi-device, the Internet of Things and Brillo. So we've already started to talk about what you can do on Wear and what you can do on your phone. But what happens when you add Auto and Nest and Brillo into the mix? 2 really interesting things happen. Number one, the ways that you can sense the environment can change. And that means that our ability to understand context becomes much more richer, and we can do a much better job. Secondly, you have a much greater surface area to surface the benefits of location and other contextual signals. So imagine, for example, that you say, turn on the lights. Well, we can answer that question now because what you can do is you can know exactly which lights to turn on because we know your location very accurately. So that's a really exciting thing. The final thing that I want to talk about is opening up that flexible, always-on computing platform. So through this talk, we've talked about this analogy between the human brain and human sensors, and I really want to talk a little bit about what we might be able to do. So historically, what happens with the human brain is we have the cerebrum and the cerebellum, and they're like our powerhouse processors. That's what we use to understand language and what you're using right now to understand what I'm saying. But there's this other part of the brain that many of us are not aware of called the brainstem. And the brainstem is the thing that makes sure that you're breathing when you're asleep and wakes you up when there's a loud noise, like an alarm, and wakes you up when the lights are bright, and wakes you up when you fall out of bed. That system is always running, even if you're sleeping. This should look familiar to you because it's exactly the same diagram that I mentioned earlier. You have this low-power subsystem that gives you the capability to process signals, and it's always on. But what's incredible to me is just how capable these low-power subsystems are becoming. So what I did is I compared what's called a sensor hub, and in this particular case, it has the romantic name STM32F411. This is just one example of one of these devices that can provide this low-power hardware capabilities. There's lots of different designs. Sometimes it's in the sensors. Sometimes it's in the same piece of silicon as the main application processor. But what I did is I wanted to compare it with a Pentium of 20 years ago. Now, believe it or not, the Pentium of 20 years ago has about the same computing power as one of these low-power hardware processors. Now, I got to remind you that 20 years ago, we still had the internet. We still sent email, we still browsed the web, we still put together documents. And so this chip at 100 MIPS was able to provide a pretty good user experience. Now we have that same amount of power just to process the sensor measurements, which is like really mind-blowing to me. And then the other thing to think about is just how much lower power they are. Let's imagine that I could shoehorn a Pentium into your phone. Do you know how long it would take to flatten your battery? You do the math, and it's like 30 minutes max. But you take one of these STM32F411s, there's a mouthful, and you plunk it in there, and you can basically, it's so low power that you can basically just keep it running all the time. And if it was the only thing running on the phone in typical mode, your phone battery life would last for 60 days. Now, I want to remind you again, I think we all know what Moore's law is, but it's just fun to look at this again. So this is the Intel Pentium from 20 years ago, and this is the STM32F411 that's in some of your phones right now. And it's crazy how the difference in size works. But here's what I'm super excited about. What happens when instead of this processor being a fixed function that the developer who makes the phone gets to decide what runs on there, and we open it up to third parties and allow us to develop the code in a dynamic way? Think about what happened with GPUs in the 90s, when all of a sudden, instead of having a fixed pipeline, you could do flexible things and render really interesting things. What if we connected not just accelerometer and gyros and compasses, but entire systems so that even when the phone is like in low power mode, it can communicate with nearby devices using Bluetooth low energy? This is something that I'm incredibly excited about. And just to convey the power of what this idea means, let's look at some concrete examples. Suddenly think about it. All the things that, this whole discussion that I'm having with you about lower power would almost become irrelevant because you now have a platform to make things really, really low power. And what you could do is you could take that indoor location system and even in a deployed phone, make it run at low enough power that you could have it always on. Not only that, but you could even detect sensors the same way that we talked about the brainstem. You could detect falls, like when you fall out of bed. You could detect earthquakes. You could detect even car crashes and be able to offer the user help. Now, that's in the phone, but when we come to wear, it becomes even more incredible. Because what we can do is you might be able to walk up to a door and just knock on it, and your phone would detect your knock, and it would talk to the device over BLE and unlock it magically. You could even do weird things, like imagine that you're into juggling. Anytime you could juggle, we could detect that and give you statistics about how often you juggle and something like that. And perhaps just to twist your brain a little bit, one of the really interesting implications for me as an old-time RPG guy is that we could build a location-based game where you literally cast spells. So as I do things like this or like some other symbol, we could build a game around recognizing when you make those symbols in real life. It really does open up the exciting possibilities to be able to access that platform. And with that, I'd really like to thank you for your attention today. I think we're at a unique part of the history of computing now with these abilities to combine the sensing, the computing, and communications ability. And we can use these to simplify users' interactions with the device. We've added a bunch of rich APIs. We hope that you use them. We can't wait to see what you folks will build to make your apps context aware. Finally, Marc and I will be standing outside to answer questions after this. And we have some special talks about the Places API and Activity APIs tomorrow. And we'd love to hear your feedback and thoughts at this page. Thank you very much for your time today.